everybody. This is the fourth video on the engine build series, the small block Chevy that I'm putting together. I've got big updates, so we'll just kind of get into them. First, the machine shop has got a hold of me. The block checked out okay, no cracks, nothing deformative that would prevent it from being reused. They were good to go with a 30 over, so the cylinder wall thickness and the taper and run out on it was good enough that a 30 would clear it all out and have nice straight cylinders for the new pistons. They told me that the crankshaft bore was straight enough that it did not need an align hone, which was good. Saves a little bit of money, but mostly just lets me know that the block wasn't overstressed and the crank wasn't warped or anything like that from its previous use. So that's all good news. They did verify that it's going to need some decking. There's warping in the cylinder decks, and they're going to go ahead and do a flat surface machining on the cylinder head surfaces and have it nice and squared so that with the new heads and new head gaskets go right on flat, tighten up right, no leaks hopefully. So that's all great. The bigger part about that was, now that they know that the 30 over is sufficient to get the block into a usable condition, they need the pistons to be able to actually piston match to the cylinders. So I got to order my first real parts for the engine. And I don't know if you can see the camera, but there's a box down here, and it's got the rotating assembly in it. Crank, pistons, rods, bearings, and rings. So everything you need to build the lower end of the motor. So we'll go ahead and take a look at all that stuff here in the box. This is the Eagle rotating assembly kit. Got it from Summit Racing. Cost about $620 plus tax, minimal shipping. And it arrived within about 4 or 5 days after ordering. It actually was a pretty dang good deal. We got one of the pistons out here. These are hyper eutectic pistons, which means they have a high silicon content in them with the aluminum. That helps with the heat transfer, and they don't expand as much under heating. So you don't have to worry about cylinder binding as much in the bores as these get really hot. I was surprised. It said in the description of the kit that it had floating pins, but it was not assembled, but they came assembled. So that's money I'm going to save right there, because the machine shop's not going to have to heat up these wrist pins and connecting rods and press them in. So that's already done. Nice with the shaky sound on it. So another good thing about this isn't unique to Eagle. Almost everybody making pistons now is putting this Teflon type skirting on it to help with it sliding through the pistons, less friction. So that's that silver titanium pewter or whatever insert color here look to it. So they do have the skirt protection on it. There's your ring grooves right there. Top compression, second compression, and then the oil scraper and the 2 oil rings go in this bigger channel down here. Now, one thing about these rods, they're not high performance, but they do say they're rated up to 500 horsepower. The first thing I noticed on them is that these are not cracked rods. These were not cast or forged. They're cast rods, but either way, they were not made as one piece. So they don't have the cracked separation joint. These are just kind of put together as one or 2 different pieces and then bolted together. So they're not technically as strong as cracked rods, which are matched to each individual casting. They'll cast the lowers and then the rods themselves separately, and they just, I guess, do light machining so they're flat and fit together. They do have some, I don't know if these are ARP. Let me read on these. They do have ARP bolts, connecting rod bolts right there. So those are really nice. Everything I've read is these pistons work great. For anybody that isn't trying to like blow through the quarter mile at warp speed, these things make great street strip little pistons. So that's why I went with them. Came with a ring set. Now these are steel moly. They're not chromoly rings. These will be fine. I'm not going to do any real boosting with these rings or anything like that. So I can accept a little bit of expansion with heat, and I'll just gap them if I think I want a little extra protection. Instead of going like 16 to 18 thousandths on the ring gap, I'll bump it up to 20, 22 thousandths. I'll file them off a little bit just to get a little extra protection. Make sure they don't bind up if I do get really saucy with it at some point. Hastings rings, which I've heard of before in my limited experience with engines. I know the manufacturers, and Hastings has been around for a long time, so I have no doubt these rings will be good. It's got the 3 different sets. I haven't cracked any of this open yet. All the top rings are here. And you got your second, well, these are your oil rings. This is the, so I always call these the wiper. It's that, those little squared groove rings. I always called that the oil wiper for some reason. But anyway, they're there. Here's your second rings right there. And then the oil rings that go on top and bottom of the wiper are down here. So got all the rings. It also came with bearings. Now, the King, I have not necessarily heard of as a bearing manufacturer. And I'm not sure these rings or these bearings are the ones that are going to end up in the car. I may step up to better bearings. I'm going to do some research on them. I don't even know what these are made out of, if they're just aluminum bearings or they're whatever other type of material they use to make bearings. Just going to have to get on the interweb and see how these rate out. If I can find bearings are so important. You do not skimp on bearings. And if I can find a better set, I'll probably get those and just set these aside or sell them or whatever. So anyway, those are the main bearings. Then we got the rod bearings right here. Same manufacturer, same material. So same deal. I may step up for better bearings all the way around on this car engine. Then the other part of the rotating assembly, down here, there's our brand new crankshaft. Look at that guy. I am not going to take this out of the plastic until it's absolutely necessary. I do not want to, in any way, shape, or form, damage this thing. So it's a nice, new, cast steel crank. Heavy as hell. I'm not going to move this at all. I'm not even going to think about it. I'm actually currently hurt right now and under some doctor's care. My back is messed up, but so I'm not going to be doing anything silly. But let's see if I can get this. I don't know if I just noticed this when I was looking at it, but the oil journals in the crank have a nice chamfer on them. I don't know if that was ever done from the factory, and that's always what I thought was somebody did after the fact. It's kind of a hot rodding tip. If it is, then they've already done it for me. If not, and I'm just mistaken and never noticed that that's the way oil galleys look on cranks from day one. I just never paid much attention to that part. Now this is an internally balanced assembly. They say it is, and I'm going to take their word for it because I don't want to spend a whole bunch of money and time weighing out the rods and doing the bob weighting and getting the machine shop to grind and match and all that. They say it's internally balanced, taking their word for it. It says right on the website that you can get a neutral balanced flywheel and a neutral balanced harmonic on the front. You'll be fine. So that being said, we're just going to leave it the way it is and just assemble it as it came out of the box. Now, I get to do some long-term thinking now that I know what the engine block is going to be. It's going to be a 355. It's a 4030 with a 348 stroke. So I can start thinking about what my compression ratio is going to be. I had these grandiose desires with this engine to maybe build it for boost. I'm giving up on those, so I think I'm just going to cheat up the compression ratio when I put this thing together to get the most out of it naturally aspirated. So on compression, I've started to think about it now that I have these numbers and I've got things set up here on the board. With a 4030 and a 348 stroke, I am going to use 64cc cylinder heads instead of the 72, so that's going to give me more compression. These pistons were 4-valve reliefed, so they are technically dished, not domed. They have an extra volume built into them where the recess for the valve relief was cast out of them. Each one of them is 7 cc's bigger than a true flat top. So I got plus 7 cc's. The deck height, now I mentioned that the machine shop had said that they're going to have to do a little bit of milling on the head decks. This for .025 25 thousandths or 2500ths, I mean, is the normal deck height on a small block Chevy. They said they're going to have to take 2 or 3 thousandths off that, so that's going to leave me somewhere in the neighborhood of a 22/100 inch deck height. That'll be the distance between the top of the piston and the top of the engine deck. That's not the quench. That doesn't include the cylinder volume and all that, cylinder head volume and all that. That's just the height between the top of the piston travel and the top of the deck. Then head gasket thickness is basically all I have left to play with to determine my compression ratio. So with these numbers, if I use a 45/100 head gasket compressed thickness, I'm going to end up with a 955:1 compression ratio. If I use a 40, I'll get a 965. If I use a 35, a nice thin head gasket, I'll end up with a 976. Probably going to go somewhere in the neighborhood of this 40. End up with a nice even 965. That's going to be pump gas friendly, at least for 91. I'm not going to run 87 on it with a 965, but I can run 91 octane all day long and not have to worry about knock. So, and that should produce a fair amount of power. It should get me in that 390 to 410 horsepower range that I'm really shooting for out of this motor. Then there's other things to consider that I'm going to have to think about. I've already kind of half calculated this is the static compression ratio, by the way. And there's 2 different compression ratios, your static and your dynamic. Your dynamic compression ratio is affected by your camshaft. And you have to take into consideration the intake valve closing point on your cam, because as the piston's coming up, if your cam profile is allowing your intake valve to stay open on some overlap, you're actually going to be pushing out some of the air that could have been compressed back up into the intake system, into the runners, and you'll lose some of the fuel air mixture that you can compress and explode. So your dynamic, in most circumstances, your dynamic compression ratio is lower than your static compression ratio. So if you're running, and it's actually, that's the dynamic one is the one that really matters when you're talking about whether or not you can run high octane fuel or your boost. So you wanted to run turbo supercharging. You're like, oh man, I really want this nice 10.5 to 1 engine, but I'm worried about it, blowing itself up. Well, go do the math and check your dynamic compression ratio. If you choose the right cam, you're going to find out that 10.5 to 1 engine is actually probably somewhere closer to 9.5 to 1. Standard IVC intake valve closing point at 50 thousandths lift on a cam is like 41 degrees, which means 41 degrees of cam rotation on that lobe. You're getting the valve's still open while the piston's starting to come up, so you're pushing some of that potentially compressed air out of the cylinder, and it's lowering your overall compression ratio. It's getting a little advanced, and I understand it, but I'm also not going to, sit here and dwell on it too much with this little video. This is mostly just an update about what I'm going to get out of this motor. But you know what? I'm going to pause here. I'll just maybe draw a little demonstration of what I'm talking about that dynamic versus static compression ratio. Okay, so I'll talk about the dynamic versus static compression ratio again. In a dynamic compression ratio, you add 2 more variables to the list that was on before for static compression. And those are your rod length and what's called the IVC, or the intake valve closing point. IVC is usually measured at 50 thousandths. Like everything else, it seems that's just a standard. There's nothing particularly important about that number. That's just where the industry has agreed to do all their measurements for commonality. So you can compare apples to apples between cams. So everything's measured at 50 thousandths lift. Now here you have a cylinder head, valve, and piston assembly. This is your intake valve, and here is your camshaft. Of course, your camshaft has a base circle and then a lobe. The lobe pushes on the lifter, lifter pushes on the push rod, elbow connects to the wrist, to the thigh bone, blah, blah, blah. Got your rocker arm here, a rocker arm ratio of usually 1.5, 1.6 to 1, which means for every 1 it moves here, it pushes down 1.5 here. So you get more lift with less travel of the push rod. You can keep shorter push rods that way. So, but as it relates to dynamic compression, if you look, as the piston travels up through its rotation off the crankshaft, there is an overlap between when the intake valve is open and the piston is pushing up. And you will see, imagine an intake runner coming off of this towards your carburetor and manifold. You will get air traveling back out of the cylinder as the piston travels up. So you lose volume. You don't lose surface area. Okay, your cylinder volume is always going to be the same. That's the maximum amount of air that it will hold. But your compression ratio of that volume changes, because the actual point in which compression matters is when this valve, in its rotation off the crankshaft, or I'm sorry, off the camshaft, closes. And now you have a sealed surface that the piston can compress the gas and air mixture, waiting for your zing-zang plug to blow it up. So if you have more of a time that this intake valve dwells open on your cam lobe, that's going to reduce your overall compression ratio and lower it to a safer limit than you actually might think you have. Now, I did this just based upon a standard IVC of 41.41 degrees, or not 0.41, it's actually 41 degrees is kind of a standard for off the comp cam I was looking at of dwell of that valve being open. At that point, off of that like 9.65 static compression ratio, my dynamic compression ratio was only about 8.5 dynamic. So that's the number that really mattered. So even at 965 to 1 static compression ratio, if I slipped those piston rings so that they're gapped a little bit wider, I could still boost this motor and not have to worry about it too much. I could probably run 7, 8, 10 pounds of boost on this and be okay, even at 965 to 1 static compression. So I'm safe that way. Still don't think I'm going to do it. It's only a 2-bolt main, and I'm not trying to throw the bottom end out, but that's just something to consider about. When everybody starts talking about compression ratio, oh yeah, I got this 10.5 to 1 motor. Do you really? When you were doing this build, did you take into consideration your cam profile? And have you looked at the amount of dwell of your intake valve while the piston's traveling up and trying to compress the air? There's other issues involved. This creates, I know a lot of you know, or you have heard about turbulence in your intake. I showed you up here about the intake coming up there. You get resonance in your intake port as you've got volumes of air trying to make their way down into the cylinder, and then you will end up with that reverse flow of air from the piston pushing it back up, and you will create a turbulent flow here, and that can actually resonate all the way up your intake and really screw up your flow. So you got like 220 cc head combustion chamber heads. You haven't done the math right. You've got the wrong cam. You're going to be throwing air back up into that big ass 220 cc runner. You're not going to get 220 cc out of your heads. You're losing power. Cam. Probably going to do a whole nother video when I get this nailed out on my cam and just show you how important it is. You can get the biggest, baddest everything in your motor, but if you have not matched your camshaft to it, you are wasting money and you're wasting power. And worse yet, you could be blowing up your motor. I'm just going to do a silly little demonstration, wipe this off, about some of these aggressive cam profiles I've seen. You know, 50 lift, half an inch lift is like the magic number. Everybody's, oh, I want to get a half-inch lift, maybe a 520 in exhaust and a 500 intake lift. Those are good, but how long is it staying open that half an inch? If you've got a nice broad lobe on your camshaft and your lifter is able to ride that lobe a little bit longer, you'll have 50 thousandths lift and more time for that air to make it into the cylinder. 50 thousandths, I'll just call it. I am so bad at this. Half an inch lift. But if you get a cam that's a pyramid, you might get 7 hundredths or 7/10ths of an inch lift. Big lift, but your lifter is just going to be like, I'm done. Congratulations, you opened it this far for 0.003 seconds versus opening it this far for 0.25 seconds. Which one do you think is going to give you more volume in that cylinder to burn? So you can get these really aggressive cam profiles, really high lift cams. Oh, I'm going to make all this power. No, you're not. You're wasting it. You got to get the cam matched to your stroke, your bore, everything. The RPM profile you want to run, you got to match it to the torque you want. Do you want it down low? Do you want it up high? Do you want horsepower instead of torque? You're going to do your driving. You're going to do your driving between 3,000 and 6,000. You're going to do your driving between 1,500 and 4,000 on the street. All of that matters, and we'll go through all that in another video. Cutting myself off here. I'm going way long on this, way more information than I thought I'd be putting into this one. But back to the cool stuff. We got engine parts. It's happening, you know, like 30 years in the making, and I've got this stuff in my hands right now. So tomorrow I'm taking the pistons to the machine shop so they can go ahead and measure them and piston match them to the bores. And hopefully that'll all be done within a couple of weeks, and I will have that block back on that engine stand, upside down, throwing that crank in that son of a gun. Another thing, leave you on this note, I'm probably more proud of this than anything. I have a clean garage, somewhat organized, and room to work. Probably the biggest thing that's come out of this is getting this garage usable. So really excited, guys. Please like and subscribe. Things are gonna be moving faster now. There's definitely steps that are within reach, and hopefully within the next 60 days, I'm gonna have myself a completely assembled motor, and we'll see about getting it up to a test cell, getting it broke in, and maybe getting some dyno numbers on it. Thanks for watching, and I will see you hopefully shortly with the next engine build video. Have a good night.